view of my own self or of anyone else or the chat. So
okay, that's fine for the chat, Stephen. So what we'll do is have your lovely talk, and then participants, if you're happy to put your questions into the chat, I'll read them out to you at the end, Stephen.
Marvelous. Okay.
Okay, well, maybe I can start just giving you a brief introduction. So next on our workshop agenda today, we are very privileged to have Professor Stephen Serjeant, who is a professor in astronomy at the Open University, who's going to tell us about how astronomy uses machine learning and AI. Thank you, Stephen.
Brilliant, thank you. I just realized it's 1 minute to 9 on my clock in UK time. Is it okay to start now, or?
I was just wondering to Zainab if we should wait another minute or two in case people were joining on the hour.
I think it's fine.
It's fine.
Okay. I think we have people back. Thanks, Stephen.
Marvelous.
Yeah,
Okay. Okay, well, I'll kick off then. So I'm going to talk about machine learning, AI, in astronomy. And I wasn't asked to put AI in the title, but I thought I would anyway, because it's a bit of a bugbear of mine. I believe the term artificial intelligence is industry hype, because I don't believe there is any underpinning intelligence in any machine learning technologies at the moment. And I cite as evidence this AI generated image of a woman going camping, and I don't know if anyone can spot the fundamental error in this image. So I mean, what the machine learning is doing is it's putting together textures and colors and patterns in a way that matches its training set as best as it can, and it's generated an image, and it's got no physical understanding. It doesn't know that there's a campfire inside a tent. So if you're going to say AI, I think artificial idiocy or something, artificial idiots. So that out of the way, what I'm going to talk about are my own first forays into machine learning, then astronomy's big data problem, and I'm going to focus particularly on the phenomenon called gravitational lensing and also convolutional neural nets. I'll talk about crowdsourcing the labeling through citizen science, Galaxy Zoo, and a big foundation model called ZooBot, and talk about how we apply ZooBot in gravitational lensing, and also to look at clumpy galaxies and some other machine learning technologies that we use in that case. I'll also talk about a different way of looking for gravitational lenses through infrared astronomy and some deconvolution techniques that we've used, and then talk briefly about some other astronomy machine learning, and I'll wrap things up. I can't make this a comprehensive overview at all because it's just vast. There are so many applications of machine learning in astronomy. So, but I will do my best to highlight some particular areas that I've found quite interesting, quite stimulating. And a lot of these will be inevitably from our own research group at the Open University, because these are things that we think are really fun and exciting things that we're doing. I don't have a picture of the entire the machine learning group, but this is a picture of the Cosmology Coffee group that we had our 15-year anniversary of Cosmology Coffee last year, and we made some pictures. So some of the people whose work I'm going to be talking about in this talk are in these images here. So I'll start off with my own first forays into machine learning, and this started, in fact, when I was working at a different University of Kent. And the problem was to estimate photometric redshifts using a technique called genetic algorithms. And I was collaborating with a computer scientist there called Alex Freitas and his student Nick Miles. So the problem is to estimate the the redshift. A redshift is a measure of how far away a galaxy is. And I can go into the physics of that if you like, but I'm going to just keep this at a relatively low level, astrophysically speaking. So the idea is the problem is to measure, to estimate the redshift without getting a detailed spectrum of a galaxy, but just use its colors. So I've got a plot here of a spectrum of a galaxy. That's the line here. The x-axis is wavelength, and the y-axis is actually a logarithmic measure of flux. And what you measure are these big data points. The redshifting, when it happens, is moving all the observed wavelengths to the red. So the redshift moves the spectrum to longer wavelengths. So if you look at the spectrum, it's got a number of discontinuities. I think in this case, these are Lyman break discontinuities, Lyman limit. But fundamentally what's happening is the spectrum is shifting to the right, and these discontinuities are shifting, and so your big wide data points, your big photometric data points are then shifting. So the leftmost ones go down first, then the next left, and then the next left, and so on. And so from the color, from the ratios or the differences of these fluxes, these flux measurements, they you can derive an estimate of the redshift of a galaxy, and it kind of works. It kind of works. The more of these bands you have, more of these measurements you have, the better it works. I've got some examples here of some photometric redshifts against the exact spectroscopic redshift measurements, and you can see mostly it works, but you get a few catastrophic outliers where it fails very, very badly, and we've got some more outliers here. And often this is down to misinterpreting one of these discontinuities as a different discontinuity. So the idea was, can we do better than just the minimum chi-squared fitting of the fluxes? And the idea was to use genetic algorithms. So the idea was that we can create a decision tree to find these failures. And if we do that, we could use more information than just the fluxes or the color. So we could use the sizes, we could look at the neighbors of the galaxies, all sorts of things. Color gradients in the galaxies, anything. So then we might be able to identify these catastrophic failures, and then we can get better estimates of the redshift of how far away the galaxies are. So we used genetic programming. The idea here is to evolve a population of decision trees using mutation and crossover. So I've got an animation here that I stole from Wikipedia because I actually think it's a really very good animation. So this is a decision tree where you have crossover, where you take a chunk of a decision tree and move it to another decision tree. And we also have mutation, so you might change a greater than to a less than or whatever. The problem is, as a surface you want to optimize, it's quite spiky to find the minimum. So for example, swapping a greater than for a less than completely changes the decision tree. This is mitigated by having many different trees in each generation of trees. It worked, sort of worked. Well, it worked better than a benchmark computer science decision tree from 2005, but it was kind of tricky to work with. But there is a better way to optimize, to explore function space, and that is neural nets. Now, I gather you have had an introduction to the fundamental machine learning technologies earlier in this seminar series, in this workshop. So I won't go into too much detail, but I just wanted to just give a very quick broad brush overview of the technologies. The idea is you're making a computer science analog of a physical neuron in a brain, for example. So you have a bunch of inputs which are labeled x1, x2, x3, and so on. You do a weighted sum, and that's illustrated in the equation to the right here. You do a weighted sum, the wi's are the weights, add a constant offset, the bias parameter, and then stick this all into a nonlinear function. It's called an activation function. Actually, there's a lot of flexibility in what you want that activation function to look like. It could just be a step. It could just be, if it's bigger than this, return a 1. If it's less than this, return a 0. And then you have this output. So the nice thing about this is that by stringing these neurons, these artificial neurons together, you can approximate any function, subject to some fundamental mathematical constraints like, I don't know, differentiability or something. But from the perspective of a physicist, that's fine. That's fine. So I'm going to give you a physicist's illustrative proof of this universal approximation theorem. This would not satisfy a computer scientist. This would not satisfy a mathematician. It barely satisfies a physicist, but it's, you know, it's good enough. It's good enough because, I mean, fundamentally, my approach to these technologies is I want to use them to do interesting things. I'm not quite so fired up about the fundamental computer science development or the pure maths or the linear algebra or whatever. So, so here's a very, very quick physicist's level proof. So let's imagine you have one input, x. We'll stick it into 2 neurons. One's a step function and the other one's a step function. That's what it sticks what they output. And let's make the steps slightly offset. We'll multiply 1 by -1, and then you get a little box. Okay, so you can turn your input x into an output box. Okay, now if you string together enough boxes, you can approximate any one-dimensional function. Okay, so I mean, subject to some obvious constraints, but for the functions that we want to explore in physics, fine. I mean, this is just fine, and it generalizes to higher dimensional functions as well. This is the universal approximation theorem. This is pragmatically a much easier way, a much better way to explore function space than the genetic programming that I was doing before. The downside is you get a lot of weights and lots of these W parameters, a lot of numbers to optimize. So that becomes a fundamental computer science problem. Optimizing these weights and these biases, it's a linear algebra problem, it's a computer science problem. It's solved by calculating numerical derivatives, and that's through a technique called backpropagation, or backprop for short, and it's deployed often on GPUs. I won't go into that, you'll be pleased to hear. If you want to know more about that, I would say ask a computer scientist for details. I'm quite interested in the applications of this technology. And one quite nice application, which was developed by a postdoc at our institute, Laura Hunt. In fact, she did it just before she came to the Open University. It is to predict the ages of galaxies from their broadband flux measurements. So you might measure the fluxes of galaxies in through a red filter, blue, green, yellow, whatever, maybe into the infrared as well, and just big broadband, wideband pass filters. And from that information, knowing the redshift, but from that information, you can predict the age of the stellar population of the galaxy. And this is a very complicated function of these input parameters. If you want to do this from first principles in astrophysics, you would fit a population synthesis model to the flux measurements, and that's takes into account stellar evolution, all sorts of astrophysical effects, and it's a complicated numerical problem, and it takes a while for this sort of code to run. However, you can approximate the answers really very well with one of these artificial neural nets. You just put in the flux measurements in the beginning, and out pops very, very quickly. Out pops predicted age of the stellar population. So I think this is quite a nice application of artificial neural nets, and it's quite a good example of having to explore this complicated function space to pick up a solution. So those were my own first forays into machine learning. I'm going to talk next about astronomy's big data problem and gravitational lensing and convolutional neural nets. And it's quite interesting also that you've just had a talk on from high energy particle physicists dealing with a high luminosity LHC data. That's another gigantic data problem. These, so astronomy and particle physics are facing giant data avalanches at the moment. And I've got an article here from 2011 that the Square Kilometre Array telescope, which is being built now, will generate more data than the entire internet as it was in 2011 by 2020. Now the building has been a little bit delayed, but I mean it's still true that the finished telescope will be that scale. It's an exabyte scale data avalanche, and it's needing exaflop scale computing, vast amount, petabytes and petabytes of data just from one facility. This is the Square Kilometre Array telescope. Oh, my doorbell's going. Oh my goodness. Well, I'm going to have to ignore that one. One of the facilities that I'm personally involved with is the European Space Agency Euclid Space Telescope, and that's again a petabyte scale data avalanche. It's surveying about a third of the sky to nearly Hubble Space Telescope quality, and there's just vast amounts of data. So I've got some images here of the the Euclid Space the Euclid Space Telescope has taken of some nearby galaxies, and it's just beautiful. It's just beautiful. So, and you see all these little tiny dots. They are galaxies, pretty much. Mostly they're galaxies. They're just, oh, there's so much there. Now, a particular thing that I am interested in astronomy is gravitational lensing, in fact, strong gravitational lensing. So what is happening here is that following the predictions of general relativity, every object, every massive object in the universe is curving the space-time around it. Right now, sitting in our chairs, right, we are curving the space-time around us, but it's too small to measure. But if you have a giant, very massive object, an astrophysical object like a galaxy or a galaxy cluster or the sun, it's noticeably gravitationally lenses background objects. So I've got an illustration here from NASA website, a background source seen through the gravitational field of a foreground galaxy, and the light rays are deflected onto us, and we are at the place where it says focus. Actually, it's not quite right because the light isn't focused in the geometrical optic sense, but nevertheless, that's where we are. And so we have a single background source, which then appears as two separated images in this illustration. And I've got an illustration of a real, well, it's not an illustration, it is a real strong gravitational lens event from the Euclid Space Telescope. It was actually spotted by Bruno Altieri, who works at ESA and was just looking through the raw data as it was coming into to the European Space Agency. And he saw this, he thought, oh, I should alert the strong gravitational lensing people because this is beautiful. So what you got is a foreground elliptical galaxy and a background galaxy seen almost exactly behind the core of this foreground elliptical galaxy. And so you get 4 images of this background galaxy, and they're stretched almost into a perfect ring. It's beautiful, beautiful image. It's one of the most nearby galaxies that are gravitational lenses. So it's one of the reasons I love gravitational lensing, is that the images are just, they're so arresting, they're so beautiful. Now, most of the matter in the universe, for reasons I won't get into, but we know that most of the matter in the universe is not visible matter. It's not baryonic matter. It is, in fact, dark matter, which is collisionless stuff, and we know extremely little about it at the moment. But we can tell where it is from the gravitational effect that it has. So, for example, in gravitational lensing, there is too much lensing in general for it to be attributable just to the visible matter. So there has to be additional matter there. And the gravitational lensing is telling you where the dark matter is in the universe. And this can also constrain theories of dark matter. So how clumpy the distribution of dark matter is tells you something about the nature of the particles which are comprising dark matter. You can use the time delays between images, different images of a background object. And those time delays depend on the Hubble constant. So that's the expansion rate of the universe. So you can do cosmological measurements just using gravitational lensing. Also, if you're interested in galaxies themselves, then this lensing is magnifying the background galaxies. So it's useful if your interest is not in cosmology, but rather in just galaxy evolution. But these systems are rare. You need an almost perfect chance alignment between the background galaxy and the foreground galaxy. Now, the Euclid Space Telescope looks like it will be, well, the prediction is that we will see at least 100,000 strong gravitational lenses. And this is a factor of 100 more than we've had before. So this is just transformative for the study of strong gravitational lenses. So that's great, but Euclid is covering so much of the sky. It's going to detect about 1 billion other galaxies, 10 to the 9. So getting these 10 to the 5 strong lenses among the 10 to the 9 other galaxies is a hard data mining problem. And so the technologies that people have been focusing on have been convolutional neural nets to parse all of this large imaging data set. So it's a similar technology to the artificial neural nets that I talked about earlier. But here the idea is that you start off by, instead of optimizing those weight parameters, those W's, you start by optimizing the pixel values in convolutional kernels. And then you string together a series of these, and then you can start picking up image features on small scales and on larger scales. And you create an architecture that looks perhaps something like this. You have a whole series of convolutional kernels you optimize, and then you these are output to another series of convolutional kernels, and so on and so on. And then at the end, you spit out all of those outputs and put them into a more conventional neural net structure, like I talked about at the beginning. I've got an example here from handwritten digit recognition. So this was one of the first applications of convolutional neural nets, and one of the first big successes of this technology. Now, I was very lucky at the Open University to bump into a computer scientist called Jane Bromley. And Jane turns out to have been one of the early pioneers of this convolutional neural net technology. I would say probably her biggest or most cited contribution is in a technique called Siamese neural nets. We probably wouldn't call it that if they were invented today, but the idea is you take a signature and then you use the convolutional neural net to compress that information into a data point in a very high dimensional, very abstract vector space. And then you take another signature, ostensibly by the same person, and then compress it in the same way. And then you look at the distance between these two data points, and that gives you a measure of how similar the signatures are. So this was a technology developed for signature verification, but it's been since applied to all sorts of things, from gait recognition to a face recognition to all sorts of things. So it's been a very highly cited, highly flexible technology in machine learning. And I just bumped into her in the car park, so that's rather good. So we worked together to develop some machine learning technologies, some convolutional neural net technologies for applications to astronomy. And this is an example of one of our first attempts to find these strong gravitational lens events in astrophysical images. So we have, well, this is an architecture. This is the machine learning architecture. I've got a key at the bottom here for what all these different layers mean. And I'm aware that in the audience today, there'll be some people for whom this is extremely new, and also some people in the audience for whom this may be very obvious. So for those of you for whom this is very obvious, you won't need an explanation of what these different layers are. If this is all very new to you, I will just say that the idea is the images go in here, they go through all of these convolutional neural net, and what is output at the end is a classification that comes out at the end. So whether it's a gravitational lens or not a gravitational lens. And it worked. It worked. We did find gravitational lenses. So I've got a plot here of our early results from simulated data. This was before the launch of the Euclid Space Telescope. And the images go in, and what is spat out is a probability that an image is a gravitational lens. And so then you can choose a threshold above which to believe that a thing is a gravitational lens. So you've got a tunable parameter that you can choose to accept nearly everything. You put your thresholds at nearly 0, or you could choose to accept almost nothing by putting your threshold at almost 1. So as you tune that threshold, you change that tolerance, you get a different balance of true positives against false positives. So what you want is lots of true positives, but as few as possible false positives. If you were just picking them at random, you would get a diagonal line here in this plot of true positives against false positives. But what you want is for your curves to be getting close to the top left-hand corner of this plot, and that's what happens. So as you if you choose a false positive rate of, I don't know, 0.1, you can see that you're getting 80% of the real gravitational lenses there. So that's good. So the network is doing something useful. So it's good performance, but it's not quite good enough for finding 10 to the 5 lenses, 100,000 lenses among 1 billion non-lenses. So what Josh has been doing is he's been trying to work out what the network is responding to, because I mean these convolutional neural nets they're like black boxes. It's quite hard to understand how they're working. There is a technique that was developed at Google called Google Deep Dream, And the idea here is you've got a trained neural network, a trained convolutional neural net, and you want to understand what it's responding to. So instead of optimizing that network, you instead decide to tweak the input images, and you try to make them respond more and more and more and more to what they've been trained to look for. So I've got an example here from Google. This is images of clouds in the sky. And then it's gone through this Google Deep Dream process, and see if you can see what the network has been trained to respond to. So that's the output here. And to me, this is gloriously, it's like a weird dream. It's psychedelic. And you can see that this network has been trained to recognize birds and buildings and animals and things. So that's told you something quite useful about this particular convolutional neural net. So what Josh did was try to do the same technique on boring, unlensed images of galaxies. So this is a boring galaxy which has gone through this process, and you can see that the network has hallucinated a ring around this galaxy. And here's another one. It's hallucinated an arc around the galaxy. So it seems that this network is seeing rings and arcs. It's looking for rings and arcs. So it's sort of doing something physically sensible, but it's these aren't good astrophysical examples, but it tells you something useful about what the network has learned to respond to. So that's where we were just a few years ago on convolutional neural nets and looking for gravitational lenses. What I'm going to talk about next is citizen science and Galaxy Zoo and a big foundation model called ZooBot. So I'm going to make the case to you that citizen science, well, human beings can do things that there is absolutely no machine learning technology can do at all. So I want you to imagine that you've been tasked with doing face recognition in crowds of commuters. Let's say, I don't know, you're a shopkeeper, let's say, and you want to look for people who are doing notorious shoplifters who want to steal from your shop. So you set up a camera and you set it up to do real-time face recognition, and there are off-the-shelf machine learning models you can use for this. It's not a terribly difficult thing to do. So you do this, and now I'm going to show you the picture that one of the pictures that your camera reported, and here it is. Now, if you were a machine learning model, you just go face, 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 right? But a human being will look at this and say, there's a clown in the middle of the crowd. Why is there a clown in the middle of the crowd? So human beings have an ability to look at the data and take a step back and say, you're asking the wrong question. You're looking for particular shopkeepers, but there's a clown. So human beings can take a step back and unask the questions in a way that machine learning absolutely cannot. And there's not really very much prospect at the moment, certainly in the near future, of machine learning getting anywhere close to that. So what we've been doing is we've been trying to look through these beautiful images, Euclid images of galaxies in our first observations, and looking for these rare alignments, these strong gravitational lens events. And I'll zoom in here on the image of a Perseus cluster. There's just so many dots here. So many, they're all galaxies. In fact, I had to compress this image slightly because otherwise I wouldn't have been able to do the zoom. It would have, the PDF, the PowerPoint file would have been too big. But there is a lot to examine. There are lots and lots of these galaxies to examine. So the Euclid strong lensing experts decided to look through just the brightest galaxy, the brighter galaxies in these early release observations, and I was part of this. We looked at 12,000 galaxies, looking for these beautiful gravitational lens events, and oh, it's hard work. It's hard work. After a while, you start seeing them everywhere. You look at a piece of bubble gum on the pavement and you think, oh, is that a gravitational lens? No, no. Anyway, yes, it was a long and exhausting effort. And we classified systems as definite lenses, probable lenses, and possible gravitational lenses. And these are the results. These are lens candidates that were extracted. And so it's a small amount of real gravitational lenses, but you know that they've come from a set that has been examined by about a dozen experts. And so you know that there's this is quite a robust sample. Of course, there could be plenty of things there that the experts had not expected and might not recognize as a lens, but that's another story. This is not, in fact, the first time that a crowd of people have been asked to parse images of galaxies. In fact, the most recent big pulse of activity in this comes back to a paper that was written in 2007 by Michael Longo. He had a very bold claim. Does the universe have a handedness? ? And the claim in the paper was there was a slight chirality to the universe. So he was arguing, I forget which way around it is, maybe it was arguing there were either more anti-clockwise spirals than clockwise spiral galaxies, or maybe it was the other way around, I forget. A very subtle statistical effect, and part of the way that he derived this result was analyzing the direction of the spirals with some computer vision, with some image processing. And so I thought the way to resolve this, to be short, because it would be an amazing fundamental result if it's true, the way to resolve this would be to examine all of these galaxies by hand. And I wrote that on my whiteboard in 2007. I thought, eyeball 100,000 galaxies. And I write a lot of things on my whiteboard, things that would be nice to do if I only had a spare few months or something. And no, of course it never happened. But another team of astronomers spotted the same thing, and they had a much better approach. Their idea was to ask the public for help. So the task was an even bigger task: classify 900,000 galaxies. And they figured it would take an expert 3 to 5 years, even working 24 hours a day, 7 days a week. So they put out a call for volunteers, and they expected 20 or 30,000 volunteers. But what they got was 100,000 volunteers who have made 40 million classifications. It was a phenomenal runaway success. This project was called Galaxy Zoo, and it's since spawned a whole suite of crowdsourced data mining, data annotation, data classification tasks in a platform called the Zooniverse across all scientific disciplines. So it tapped into an amazing appetite by the science-inclined public just to participate in scientific discovery. And the scale of it and the dedication was a huge surprise to everyone. To classify a galaxy, the trick is to break the question down into a lot of small, simple questions. So this is an example of how Galaxy Zoo volunteers are asked to break down the classification of a galaxy. And what you will see is at the bottom here, we do have a question as to whether it's a gravitational lens. I've got a slightly more recent decision tree, volunteer decision tree, done by my postdoc, James Pearson, in a big project looking at galaxies imaged by the Subaru telescope in Hawaii in a field at the North Ecliptic Pole called the Euclid Deep Field North. So again, we look for gravitational lenses as well near the bottom. So we've got a bunch of classifications, including gravitational lenses. So this is a great place to start for training machine learning. So a colleague of mine, Mike Walmsley, took the Galaxy Zoo classifications, in fact 14 years worth of Galaxy Zoo annotations and 847,000 images and over 100 million classifications, and used these to test out scaling laws in training large machine learning models. So what he found was that adding more labels always helps. So no matter which machine learning model you use, and he used a bunch of famous off-the-shelf architectures, if you add more labels, you get improvements. But the size of the model only helps so far. It plateaus after about 100 million parameters. 100 million parameters. I can hardly believe I'm saying that. It's just oh my goodness. So this was quite a nice resource. So he's trained these machine learning models for trying to reproduce the human classifications that have come out of the Galaxy Zoo Citizen Science Project. So the next question then is, can this be used to find these gravitational lenses? And so this is what my graduate student, Ruby Pierce-Casey, has been doing. So again, I've got a plot here of false positives against true positives. And what you want is for the curves to be crunched up against the top left-hand corner of the plots. Okay, the random guesses again are the diagonal line, which is marked here in yellow. And I've got some example competitor networks. So these are people who have developed machine learning models, convolutional neural nets, for finding gravitational lenses, but just based them on their own simulated data training sets and whatever else they could find. What Ruby managed to do is this curve up here. This is a machine learning model from this Zoobot that Mike Walmsley developed. It's called EfficientNet B0. And what she did was she just took the very last layer and retrained that for, is it a lens, is it not a lens? And it turns out that that vastly outperforms all of the other networks. And I think the reason for that is it's based on a model that's trained on 100 million human classifications, and it's very, very hard to do better than that. So I've got a slide here that was created by Ruby. So these are the Class A, Class B, Class C gravitational lenses that I showed you earlier, that from the human eyeballing effort. And you can see if you pick a threshold of probably a lens probability greater than a half, you get pretty much all of them. And this table here, or this plot here, is the crucial one for finding gravitational lenses. So the column here for gravitational lenses is here. So we have 61 true positives, and this is in a real Euclid data set, but in among those, we also have 547 false positives. If you look at the false positives, they look like galaxies. They don't look like gravitational lenses to an expert. So there's more physics that can go into this. So this can still be improved. We've got about a 9-to-1 or 10-to-1 ratio of true positives and false positives. So to get most of Euclid's 100,000 gravitational lenses, we will have to look at 10 times that number, well, about 1 million candidates. So these are the things that will be output by a network like this. Now, 1 million is a big number, but you've seen we've already done that with Galaxy Zoo. This is a plausible sized project. So with a combination of this ZooBot foundation model and humans checking the outputs, we've solved the problem of finding these rare needles in a haystack, these rare 100,000 gravitational lenses. So I'm going to talk next about another application of ZooBot, which is through clumpy galaxies. So I've got a plot here made by my colleague, Dr. Hugh Dickinson. So this is a plot of the number of stars that are forming in the universe per unit volume. And it's as a function of redshift along the bottom axis. So today is redshift 0. And as you go to redshift tends to infinity, you get to the Big Bang. And I've got look back time along the top as well. And in this number of stars forming per unit volume, we're already dividing out the expansion of the universe. So that's been factored out here. So you're not seeing any effect from just the expansion of the universe in this plot. And what you find is that the amount of stars forming reached a peak about 10 billion years ago, and it's been declining ever since. Okay, that peak has gotten the name cosmic noon, and the amount of star birth that's been happening in the universe has been declining since that cosmic noon. And remember, all of the heavy elements in the universe get formed by or through stars. Okay, so this is the formation of everything. This is the formation of stuff in the universe. This is a really very important and fundamental plot in astronomy. So why does it look like this? Why did it go up and why is it declining again? Well, one of the clues is that there are many clumpy galaxies near the peak, but today there are very few clumpy galaxies. So if we can measure, we can find the clumps, we can measure how much clumpiness is going on, we might be able to unpick some of the physics of what's driving this. And so Hugh created a citizen science project, another citizen science project, asking for volunteers to identify clumps in galaxies. And so you might have a galaxy like this, and you might be looking for star-forming clumps of galaxies like this. So in these clumps, there's a lot of stellar birth going on. And you might want to have volunteer annotations that look like that. But what you get are volunteer annotations that look like that. You get lots and lots and lots of false positives. But these volunteers, they're false positives, they're not correlated with each other. So what Hugh did was create an aggregation algorithm to find the consensus annotations between the volunteers. And so this was published on in monthly notices and on arXiv, and it takes a plot like this and it turns it into a consensus plot like that. So we've got a way of taking the human volunteer data and creating consensus. I mean, citizen science data does often sound like, hey, free data, marvelous, let's do that. But you've often got to work to clean up the data, to find the consensus, and so on. It's only free insofar as your time is free, your own time. So this was very successful. They found 35,000 clumpy galaxies and 100,000 clumps, released a catalog. So then the question is, can we use machine learning to use these labels with machine learning to automate the process of clump finding? And the obvious technology here is region-based convolutional neural net. And the outline of the technology is like this. You start with an input image, then somehow you create regions of interest. Then you classify each of those regions of interest using a convolutional neural net. So you might say, oh, is this a cowboy? Is this a hat? Is this a horse? Is this a dog? Is this a cat? Whatever. Is this a banana? And this is this was a very successful technology. It does require multiple passes over the image, so it's been optimized through a technique called faster RCNN. So it reduces the computational overhead. So you have convolutional layers here, which create a region proposal network. Then these regions are classified. And we have a graduate student here called Jürgen Popp, who's done a phenomenal amount of work on this, on clumpy galaxies, using a faster RCNN trained on the citizen science classifications. And again, the trick has been to use the Zubot model as the feature extractor, as the first layer here. So he took the Zubot model and then again retrained the final layer and created a regional proposal network. And it works phenomenally well. It's another great success of this Zubot Foundation model. So I've got here some example outputs. So we are going here from ground-based data to better ground-based data to space data with the Euclid Space Telescope. And in technological terms, we're going from the citizen science labels to using faster RCNN, which are these boxes, and then to mask RCNN, which is another technology which I don't quite have time to talk about, but it's getting you the shapes of the clumps as well. So this has been very, very useful, and it's given us some important astrophysical insights. So it turns out that the clumpiness is tracking, the amount of clumpiness is tracking the cosmic star formation history. And the stellar population ages suggest that the clumps appear to be migrating inwards to contribute to galaxy bulge assembly. So we're getting some nice physics out of this machine learning and citizen science as well. And another application of machine learning to clumpy galaxies has been with conditional generative adversarial networks. And this is done by a grad student, Ruby Pierce Casey. So the idea here is you have data from the James Webb Space Telescope, and that is very, very, it's a very expensive telescope, so it's very precious data. So if you can predict some missing data, then you're making enormous savings, and you also create the ability, if you have all of the data, to find anomalies. So the idea here is you take the short wavelength data from the James Webb Space Telescope and try and predict the longer wavelength data. And here what we've got, we have a network here we call a generator network. This is a convolutional neural net that compresses the data down into let's say a point in a very abstract vector space, and then uncompresses it to create a prediction. That's technology is called a UNet, or an encoder plus a decoder. And the output here is a prediction of the longer wavelength data. And you can compare that to examples where you actually have the longer wavelength data. And then you train a machine learning, another separate network, to see if it can distinguish the predictions from the reality. So these networks are in competition with each other. So this is why it's adversarial networks. That's why they're called adversarial. So if you have data at the short wavelengths and the long wavelengths, you could use that prediction to see whether the long wavelength data is in any way anomalous. And there are lots of weird things in JWST data, so it's definitely a thing worth doing. And The network works extraordinarily well. This is an off-the-shelf network called Pix2Pix. We've got the short wavelength data here, the actual long wavelength data in the middle, and the generated image on the right. And it's worked astonishingly well, I would say. And this was just a warm-up project. She arrived and wanted to just get to know the machine learning technologies, and came up with this idea herself. So I would say it's a very hard thing as a new graduate student to come up with your own research project. So that worked very, very well. I've only got a few minutes left, so I will just quickly talk about infrared gravitational lenses and deconvolution. So you remember at the start of the talk, I was talking about redshifting a galaxy and shifting the spectrum to the right. So here I've got not just the optical spectrum of a galaxy, but across a huge range of wavelengths, from ultraviolet all the way up to radio. Okay, so we're taking a galaxy and we're imagining pushing it to higher and higher redshifts, to further and further away. And you can see that the galaxy is getting fainter as it gets further away, so it's going down vertically, but it's also shifting to the right. Okay. Now, if you're working at the left-hand side of this plot in the optical or ultraviolet, you can see that it gets harder to see distant galaxies because the spectrum is going down. But it also gets harder to see galaxies because the spectrum is moving to the right. So both of these things are making the galaxy look fainter to you. Okay. But if you're working on the right-hand side of this diagram at millimeter waves, or just under a millimeter, you can see that the galaxy is moving down because it's getting fainter, because it's getting further away, but it's also moving to the right, and that moving to the right is helping you. And you can even have a galaxy that is more distant, but is brighter because of this redshifting. So this is a really good way of finding distant star-forming galaxies. So I've got a plot here of the number of galaxies that you see on the sky against how bright they are. And this is a key for finding gravitational lenses. What we have is a very precipitous decline in the number of intrinsically bright galaxies. So you have a very small subset of a very large population of galaxies that get gravitationally lensed, get magnified. And so what you end up having is a population at the bright end that are dominated by the magnified ones. So you have the unlensed galaxies here in red, and a very small subset get boosted up and made magnified and made brighter. And these are the gravitationally strongly lensed galaxies up here. And my postdoc, again, James Pearson, found a gravitational lens with JWST, which verifies prediction at the faint end as well. So these predictions, these curves are quite well pinned down now. The trouble is that these infrared millimeter wave images are very blurry because the angular resolution of a telescope is 1.22 lambda over d, and you make lambda very, very big. You've got to make d very big to compensate, but it's very hard to do that. So our grad students Lunga Lauritsen, who's Lunga's now Dr. Lauritsen, and Chris Sorrell have been working on de-blurring, deconvolving these images using machine learning technology called denoising autoencoder. Again, this is the architecture that if you know what these things are, that's marvelous. If you don't, I don't really have time to explain it. The idea is the images go in and a reconstruction comes out. So we're going from blurry European Space Agency Herschel images along the bottom row to try and get to the top row here. So we want to go from this blurry 500 micron image to this truth image up here. And the generated image from this denoising autoencoder is on the left. And to me, it's phenomenal. It just looks like magic. It's so good. So we were very, very pleased with this technology. Chris has also been working on simulated data from the proposed NASA Prima far-infrared space telescope. This is its blurriest image, and this is the super resolved output, and the truth is there, and that's even better to me. It's just, I mean, you get there clearly there are some galaxies that are too faint that are not being recovered, but for the most part, it's absolutely spectacular technology. So that's pretty much everything I wanted to talk about. I will just say very quickly some of the machine learning technologies I've talked about. I haven't had time to talk about all of these, but these are some of the ones that we've been using. And the astrophysical applications, image deconvolution, image classification to find these warps in space and time for gravitational lenses, finding rare galaxy populations with image prediction, and annotations, finding star-forming clumps in galaxies. I've got a few recent publications here, and it's just occurred to me that the day before yesterday, we had a couple of papers from James Pearson that I've neglected to put up here, but if you just search for James Pearson on archive, you'll find them. And with that, I'll wrap things up, and thank you very much for your time.
Thank you, Stephen. Let's see if I can turn everything on. Thanks, Stephen. That was a really wonderful talk, and I love your enthusiasm. It's really interesting, and also to hear about all the wonderful work all the students and researchers are doing in your group. Okay, so we can open the floor for some questions to Stephen. Oops. Okay, so maybe we can start with one from Layla, who's asking, how do you deal with false positives in gravitational lens detection?
That's a really good question. It's hard, is the bottom line. So the false positives need to be weeded out by human experts for the most part. That's the fundamental problem that we have. We haven't managed to get rid of enough of the false positives. So one possibility is to just crowdsource and get a bunch of experts to look at the data. Another possibility is to get more data and try to follow them up and see if the background galaxy is at a higher redshift than the foreground galaxy. Sometimes you don't worry too much about the false positives. It may be that your science result doesn't need a completely pure sample. So it could be that you accept you've got a slightly impure sample, but you want to do something about the demographics of the population. So you don't always need a completely pure sample. But sometimes, and here's the difficult thing, the problem we haven't solved, sometimes the things that are rejected as false positives by experts turn out to be real ones, because the diversity of the universe is not it's bigger than we've been than our experience. So that's something we're wrestling with at the moment. There are types of gravitational lens that look odd and all of the experts would reject, but they are unequivocally gravitational lenses once you follow them up with redshift. So some of that's an unsolved problem, I think, is the answer.
Thanks, Stephen. Any other questions? So I wanted to ask, Stephen, what's going to be the next big challenge, do you think, in your field, that you're going to be having to develop new tools to be able to understand?
The next big, I think the next domain that is opening up is time domain astronomy. So we have a Rubin telescope, Vera Rubin Observatory, that is basically doing a movie of the sky. And it's going to be getting supernova flashes and optical transients from gamma ray bursts and gravitational wave events and so on. So that's a very different sort of data mining problem. And people are preparing for that are developing machine learning technologies now, but the data is going to be in the next year or two, and that's a different sort of avalanche that's arriving.
Yeah, exciting times. Okay, I'm not sure if we have too much more time for questions, because we will have another talk in a few minutes, and I think we should have a rest. But please join me in thanking Stephen again for that really fascinating talk. It was interesting, and it also looks like there's lots of nice things people can get involved with. Okay, thank you, Stephen, and I will speak to you soon. Okay, all right, so to everyone, we have about 10 minutes break before the next talk. So do go and make yourself a tea or get a water, and we will start promptly in 10 minutes. Thank you.